Do 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 do. And we are back to math. Hey, I hope you're doing well. Gonna go over some radians now. So what we're gonna talk about today is another way to find arc length and how to get area. Go inside of a circle. Figure out parts of the inside of the circle. How much space this part of a circle takes up. All right. So what radians are first, okay? It is another way that you can measure an angle besides degrees, all right? And it's based on how many radii it will take to cover an arc of a circle. So for instance, okay, 1 radian is equal to an angle that will cover 1 radius worth of the circle, okay? I know it seems a little bit crazy, but it's a way to relate an angle to a length more directly. And that's why they use them a lot when you're dealing with, say, like maybe how a planet moves. If you know the distance you are from, say, the sun, you could use radians to describe the distance a planet is moving. So they were invented for astronomical purposes, actually, the radians. So the concept is arc length. Remember, we've been working on arc length. Yesterday we used this formula here, which basically says that the arc length is a fraction of the total amount of degrees in a circle. All right, now if we use radians, however, the formula gets really, really simple, actually. Notice this thing that looks like a 0 with a line through it? That is what you call theta, okay? And theta here is representing, so this symbol here, theta, it's representing an angle in radians, okay? Instead of using degrees, they're using radians, all right? So if you have an angle in radians, to find the arc length, okay, all you gotta do is take your angle measure and multiply it by the radius, okay? It avoids this whole fraction dill circumference formula dill. It makes it really nice and simple. Okay, so anyhow, let's look at a couple examples then of how to figure out an arc length given an angle in radians rather than in degrees, which if it's in degrees, then you're basically converting it to radians actually, and then multiplying it by the radius. So, and one reason the relationship between these two formulas is right here, okay? Around a whole circle, it is 2 pi radians, all right? So the distance around the circle is 2 pi radians, so 360 degrees is equivalent, okay? 360 degrees is equivalent to 2 pi radians. And so, in essence, this is just converting degrees to radians, all right, and then you're getting this simplified formula. So it's actually easier to find arc length if you're given an angle in radians. So let's do a problem here showing you that. All right, so what is the arc length of JK? Okay, so first, angle that they're giving you, angle theta here, is 3/4 pi radians. All right, so for finding arc length, that would be S. Remember, it's theta times the radius, r. Okay, so theta is 3/4, I'm sorry, this is sloppy, 3/4 pi, and we're just going to multiply it by r, which is 5. So our arc length is, okay, 3/4 times 5, you just multiply 3 times 5, which is 15, okay, and you know, 5 is 5 over 1, so you have 4 times 1 is 4. So your arc length is 15/4 pi, okay? And whatever unit that would be, but we don't know the units here because it just says 5. But that could be inches, it could be feet. But your arc length is 15/4 times the value of pi. All right. What is the arc length of HK? This one's a little bit more complicated because they don't give you the degree, or not the degree, they don't give you the angle in radians of HK. So what you need to do then is figure out how many radians is HK, okay? So remember, in a whole entire circle, there is 2 pi radians. And we have 1/3 pi here from J to H, and 3/4 pi here from J to K. So HK is 2 pi minus 1/3 pi minus 3/4 pi. And I actually just put 2 minus 1/3 minus 3/4 in the calculator. I got a decimal, and I made that back into a fraction, and I got that 11/12 pi. Okay, if you hit the second FPRB button on the TI calculators that we have in class here, you can make decimals back into fractions real easily. All right, if you don't have a calculator, just make a common denominator of 12. All right, anyhow, that is how you get what theta is. Okay, that's the angle from H to K. Now, the arc length then is just 11/12 pi, and you multiply it by the radius, which is 5. All right, and so that is just going to give you 55 pi over 12. And you can't really reduce that, but that's the arc length for HK. All right. Now let's go on to area now. Let's talk about area. So we're done talking about length. Now we're going inside the circle. All right, here. Back to talk about area. Okay, and sectors, which are parts of area. All right, so here is the formula for area of a circle. Pi times the radius squared. Okay, so you've probably seen this before. All right, here you have a bullseye. Find the area of the yellow region is the question here. It has a 2-foot diameter. Yellow, except for a red bullseye at the center, it's 6 inches across. Okay, so we want to figure out the area of the yellow region. Okay, so first off, notice these units are different, and they're giving you diameters. So we have to find the radii, and we have to make sure that all the units are the same. Okay, so 2 feet is 24 inches. Let's just start by finding the area of the red circle. It's pi r squared. So what are we going to do to figure out the area? Good, you made the diameter into the radius, which is 3 inches. So 9 pi is the area of the red circle. The area of the hole, you need to convert 2 feet to 24 inches. Okay, then you have to take half of it, so that would be 12. All right, so just remember, when you're figuring out the area of a circle, you are using the radius. Okay, so it's 12 inches for the radius. All right, now, just the yellow then, you would do what? Oh, good job. You're going to subtract the two of them. Very good. The area of the hole minus the area of the red. Oops, it's hiding back there. All right, so 144 pi minus 9 pi, and there you go, 135 pi. All right. And you can multiply by pi if you're rounding it to the nearest whole number. It'd be 424 inches squared. Now remember, if you're dealing with area, you should have your answer in units squared. Okay, here is what a sector is. I've been saying it. It's just a slice of the pie, okay? It's part of the inside here. All right? You name a sector by basically the angle, okay? ACB. All right, and the center is the middle letter. Slice of the pie. Okay, so if you're figuring out the area of a sector, you're basically kind of doing like the arc length formula, where you have a fraction of the whole entire circle, and you multiply it by, this time you're multiplying it by the area, rather than 2 pi r, which is the circumference. You're multiplying it by pi r squared, which is the area formula. Okay, so not too bad to figure out the area of a sector here. So let's go ahead and do this here. All right, so first we're going to start by writing the fraction of the circle that this is, which is 100 over 360. And then you multiply it by pi r squared. Now, of course, if they don't give you the radius, you have to half the diameter. All right, so 6 squared is 36. Guess what? These 6's cancel nicely, so the area of our sector is just 10 pi meters squared. All right, now we're going to get a little bit more complicated. We're not going to go to the middle of the circle. We're going to chop off the sector with a line here. We call this line a chord, okay? But we're going to chop it off, and we're going to call this a segment of a circle. We're going to try to find the area of a segment of a circle. All right. So this is how you would do it. You'd take the area of a sector, you would subtract a triangle, okay, that you would be able to form by this line that we would cut across, that chord that I was talking about before, and that is equal to the area of a segment. All right, so that's pretty. So just think about that. Area minus area of a sector minus the area of a triangle equals the area of a segment. All right, so let's check out example 3 here. Find the area of the shaded segment. So there's going to be a lot of stuff involved here. But first, let's start with the area of the sector. Keep this little equation in mind here. Area of a sector. Okay, so remember, it's the part of the circle, 120 over 360, times the area of the circle, which is pi r squared in this case. All right, so if you reduce this 120 over 360, that's just 1/3. 24 squared is some big number, but anyhow, it all simplifies down to 192 pi. You don't want to put the pi key in your calculator here. It would just get really sloppy. You want to wait till the very, very end to put the pi key in your calculator. All right? So now is the fun part. We got to figure out the area of this triangle. So let me take my coat off here because it's about to get ugly. All right. So anyhow, whoa, we went backwards. Area of a triangle. Remember, the area of a triangle is 1/2 the base of the triangle times the height. Now, interestingly enough here, when you know one side of the triangle here, you know the other side. Because in a circle, the radiuses are identical. Radii are identical. Okay, so 24 feet. All right. Now what we need to know, and that we could call that the base of our triangle, we need to figure out the height of our triangle. The height of a triangle is always perpendicular to the base. So this is the height of the triangle right here, all right? So we have to figure out this, and we know that the base is 24, okay? Now we have to think, what type of triangle is this to determine our height? Well, if this is 120 degrees here, that means that this has to be 60, because remember there's 180 in a straight line. Okay, so we can figure out our height actually because we have a 30, 60, 90 triangle. And it's a good thing I taught you about 30, 60, 90 triangles, right? So if the hypotenuse is 24, the short side is going to be half of it, which is 12. Okay, so this part down here is going to be 12. 12, oops. Which means, as I lock in the computer there, that the longer leg is 12 times the square root of 3. That's our height. Okay, we just figured out the height. Our height is 12 times the square root of 3, all based on that 30, 60, 90 triangle principle. Sorry about that. Got really sloppy there. But the longer leg is the height of the triangle. And so we could figure out the area of the triangle by, grab your calculator now, 1/2, okay, or 0.5, times 12 square root of 3 times 24. You'll have to round that, but if you don't put the square root of 3 in the calculator at first, you could do 24 times 12 times 0.5. Then you get a more precise answer, okay? So actually don't round it yet. Wait to the very, very, very end to round it. All right, so to get the area of a segment, remember you take the area of the sector minus the area of that triangle we just figured out, and that is the area of a segment. So now you can put some stuff in the calculator, and notice I'm keeping some digits just to be precise here, but my final answer I'm rounding to the nearest tenth. Also notice my units are in feet squared, okay? Area, you're measuring what is inside of it with square units, okay? You're not measuring a length, you're measuring a square units. All right, so this is a very important slide here. It kind of summarizes the 3 things that we've talked about: arc length and the 2 ways to figure it out, degrees and radians, and then the sectors, which are the area of part of the circle, and the segments, which is an area of part of the sector, essentially. Okay, and then all the formulas. So this is a very, very important slide in case you ever get lost or get confused with the terminology. All right. And finally, here is 3 practice problems. I want you guys to give it your best shot. I will go over the answers on Thursday for these. So, anyhow, hope you guys have a great day, and we'll see you next time. God bless. Bye-bye.